Hey everyone, in this video I'm going to go over questions 7 through 12 of the USNCO 2025 local exam. You can follow along with both the exam and the solution document I've written in the description below. So let's look at question number 7. In this question we're asked, what compound can be used to remove calcium ion from hard water? So calcium ion is going to react with the anion of each of these compounds, so I'm going to go through them one by one. For A we have chloride, for B we have carbonate, for C we have nitrate, and for D we have sulfate. So for this problem you need to use your memorized solubility rules. However, I've laid it out on the right. You should definitely commit this on to your memory for the actual exam in order to do it well. So let's look at the compounds formed. We see that calcium chloride is soluble, calcium sulfate is slightly soluble, calcium carbonate is insoluble, and calcium nitrate is soluble. So we're asked what can remove calcium ion from water. So we want a compound that's insoluble, the compound between calcium ion and the anion of the answer choices, in order for it to precipitate out. So the only one that's insoluble here is calcium carbonate. So that's going to be our answer. Our answer is going to be B, because that brings out the carbonate ion. So you might be wondering, if you're more familiar with chemistry, why Mg2 plus doesn't also precipitate out. A hard water contains both calcium ion and magnesium ion. And in fact, if you look at the solubility tables, magnesium carbonate is also insoluble. So the only reason why we can precipitate calcium ion and distinguish it from magnesium ion is because magnesium carbonate needs a higher amount of carbonate ion to start the precipitation process. So if the right amount of carbonate ion is added, only calcium carbonate will actually precipitate out of the solution. So that's still going to be our answer. And if you look at the other answer choices here, none of them can reliably bring calcium ion out of the solution, since two of the answer choices produce a soluble compound and one produces a slightly soluble compound. So the most reliable choice is going to be sodium carbonate. Now for question number 8, this is much easier to do through memorization if you have the colors of some common compounds memorized from your lab experience, or otherwise it becomes like just a 5-second question. However, I recognize that some people don't have that memorized, and it's you might not know how to reason it out from here, but there actually is a way to reason it out. So first I'm going to identify which compounds are formed when silver nitrate is added to 1 molar solutions of these compounds below. So NaCl is going to make silver chloride, potassium iodide is going to make silver iodide. Now from here we can reason out the color of these compounds through a concept known as the band gap. So the band gap is the gap between the conduction band and the valence band of a substance. And if you don't know what those are, essentially the conduction band is reliant on the cation in a substance. So in this case that's going to be Ag, and it's going to be the same for both substances since they both have silver as the cation. The valence band is dependent on the anion, and in this case that's going to be the valence electrons from chlorine and iodide. Now if you look at the periodic table, you see that iodide has a larger atomic radius than chlorine, so its valence electrons are going to be further from the nucleus, and that means they're going to exist at a higher energy because it has a greater distance from the nucleus. And when a substance has an anion that has like a high energy for its valence electrons, that valence band is going to shift upwards in energy, and that's going to make this energy band gap, or Eg, smaller. And that's compared to silver chloride here, because chlorine has a smaller atomic radius. So when this Eg goes down, we see that the absorption of the compound shifts left on the electromagnetic spectrum. So the implication of this is that the compound will absorb colors closer to the visible range, and it will start to reflect the complementary color. So in this case, since silver iodide has a smaller band gap, it's going to shift more towards the visible spectrum of the electromagnetic spectrum, and that's going to result in it absorbing blue and reflecting yellow complementary colors. That same effect is not going to be present in silver chloride because its band gap is going to be bigger. So in this case, since only silver iodide will be yellow, our answer is II only. So of course, like I mentioned at the start, this problem is much faster and much easier to do. You can do it with more accuracy, like you're more likely to get it correct if you just memorize it. However, this is just a process you can use to also reason it out if you're not familiar with how to do it already. Now, question 9 is testing titration skills and general lab skills. And if you look at the problem, you can kind of break this problem down by just understanding what the goals of a titration is. So in a titration, you want to find the concentration of the analyte. And that's going to be unknown, and you're finding that with your known concentration of titrant. And you find the concentration of the analyte through stoichiometry. So in order to get the concentration of the analyte to be the most precise, you want a precise concentration of titrant so that your stoichiometry is precise as well. And one of the biggest factors in this is that you don't want dilution. So you don't want your titrant concentration to be inaccurate because then your analyte concentration will be inaccurate. So reading the problem here, we're filling the burette with 0.1 molar NaOH. So there's only really two answer choices that make any sort of sense in this problem. You don't want to add ethanol because that's just a random substance and that's not going to do you any good. And you don't want to cause an acid-base reaction with your 0.1 molar HCl. And the only real answers that we have here are distilled water and 0.1 molar NaOH. However, like I mentioned, you don't want dilution of the substance. So for the final rinse of the burette, you want to rinse it with the same substance as you're filling it with. In this case, that's going to be D. We actually do wash it with distilled water as well, but that's only for the first couple of washes so that we clear out any contaminants, and then we wash it out with the same substance to reduce dilution. So our answer is D. For question 10, this pretty much comes down to a very fundamental chemistry concept, which is like dissolves like. In this case, nonpolar dissolves nonpolar. So we're given the fact that the solute is solid iodine, or I2. And this is nonpolar because it's two atoms connected to each other that are the same atom, and there's not any polar bonds. So it's going to be nonpolar. So we're searching for a nonpolar solvent. And we can go through the answer choices one by one. Water has polar bonds. It's a bent molecule. We have OHH here. And these dipole moments here do not cancel out. So it's going to end up being polar. Ethanol, you can tell by the ol, or of course if you know ethanol, you know it's an alcohol. And it's going to have dipole-dipole forces and a dipole moment because of the alcohol group. So it's also going to be polar. So that's not our answer. Now for carbon tetrachloride, that's CCl4, which is essentially this. It's a tetrahedral molecule. So even though there are individual dipole moments with the CCl bonds, they cancel out because it's a tetrahedral molecule. So this is going to be our answer because it's overall a nonpolar solvent. D is not nonpolar, so it is polar. It's aqueous potassium iodide, so it's solid iodine with this is going to form I3-. That's not going to be the deep purple color that we're looking for. So the only nonpolar solvent here is carbon tetrachloride, and that's C. For question 11, it's also testing something really important, and that's lab equipment and lab glassware in general. You should really know this well for USNCO to do well on the exam. And if we look at the problem, it's asking which glassware would be suitable for preparing a 0.1500 molar solution of silver nitrate. So the first thing that sticks out here is that this molar value is really precise. It's to 4 significant figures. And that means we want a really precise instrument to also to be able to measure the volume of solution in order to get the most accurate molarity. So we're going to go through these answers one by one. We have the volumetric flask, which is pictured here. It's a bit faint, but you can see the line here, and as long as you fill it to that mark, the volume is going to be really, really precise. In fact, if you look at the uncertainty here, you can see it's plus minus 0.05 milliliters. So that's incredibly precise, and it's going to allow us to produce this molarity value to 4 significant figures. And in general, volumetric flasks are really good for making solutions. So yeah, that's going to be our answer, but we'll go through the other choices as well. A round bottom flask, that's generally used for mixing. It's not really used for making solutions. I mean, you could, but it won't be as precise as a volumetric flask. Same type of reasoning here. These two, they have pretty high uncertainties compared to volumetric flasks. So you don't want to use it if you're making such a precise solution like the one in the question. So our answer is going to be A. Now for question 12, this is testing a really common type of lab that you do in AP Chem, 9th grade Chem, things like that. It's a decomposition. So we have sodium bicarbonate, NaHCO3, and that's decomposing into sodium carbonate and H2O and CO2, and that's under heat. So essentially the point of the lab is to drive off H2O and CO2. So these both are gaseous, so they're going to dissipate into the atmosphere as the decomposition proceeds. So we essentially want to go until the point where the only thing that's left in the crucible is sodium carbonate. So we want the mass essentially to stabilize, and we're going to stop the heating when we see the mass is not fluctuating anymore, because that means that the reaction has proceeded fully, and heating this sodium carbonate isn't going to have any effect. It's not going to induce any other reactions. So going from measurement 0 to 1, we see the mass is still decreasing, the reaction is still happening. 1 to 2, same thing, it's still happening. 2 to 3, it does slightly increase by 0.01 grams. However, you can chalk that up to environmental fluctuations, and you're always going to have errors in these types of labs. So essentially the mass is staying the same, and we can stop it at measurement 3. So that's going to be our answer.